replication slot. So that replication slot is present on the publisher node, and it helps to like track the progress of the transaction. For subscription, we use create subscription command, and I have given an example for that. Create subscription sub and connection string. We specify the connection string of the node on which publication is created, and we specify the publication from which we want to receive the changes. Moving on to the next part, I will talk about the logical replication architecture. So when these commands are executed on respective nodes, how the logical replication is set up in the background. So suppose we have two nodes, one is publisher node and subscriber node. So when these nodes are created initially, it will already have the logical replication launcher running in the background. So now suppose in a backend user creates a publication using create publication command. So when this create publication command is executed, the publication related metadata is populated in the catalog table such as PG publication and PG publication rel. You can see the example, and so in PG publication we get the details of the publication, whereas in PG publication rel we get the details of the tables which are published. Now on the subscriber node, we will run a create subscription command. It will create the subscription on the subscriber node, and along with that it will populate the PG subscription and PG subscription rel informations, and it will also connect to the publisher node and create a replication slot which will keep the track of the LSN values while replicating. So moving on, let's see what happens. Like when create subscription command is run, so after it runs, the PG subscription will have the entry for that particular public subscription. Now the logical replication launcher runs periodically in the background, and it will check if a new subscription is created on the subscriber node, and it will instruct the postmaster to create a apply worker for that particular subscription. Once that apply worker is created, it will connect to the publisher node, and it will send a start replication command which will instruct the publisher to create a wall sender process for this particular subscription. Now alongside it, the apply worker will also scan through the PG subscription rel catalog table, and it will check which all tables, like when the subscription is created, the tables which are subscribing the changes are in init state, because the initial data of the tables are not yet copied to the subscriber node. So apply worker will scan through PG subscription rel and find those tables for that particular subscription which are in init state, and it will start table sync worker for each of the tables. And when table sync worker starts, it will connect to the publisher node and get the initial data for each of the tables. Like for each table, a particular table sync worker will be spawned. So a copy command will run for each of the table sync worker, and it will do the initial sync for each of the tables. Once it is done, the table sync will mark the entry as the state as ready for each of the tables, and then it will exit, and the control comes back to the apply worker. Now the initial setup is done. Initial data is copied from the publisher node to the subscriber node. Now whenever a incremental change happens on the wall sender process, it will be sent through to the apply worker, and apply worker will apply those changes and send a feedback to the wall sender process that yeah, this change has been applied. So yeah, so this is basically the process how the logical replication is set up. Now I will talk about the incremental change, like whenever a change is happening on the publisher node, how it will get replicated to the subscriber, and then subscriber will send a feedback, like a feedback message to the publisher. So moving on, let's see, this is the architecture, like how the tuple will move from publisher to the subscriber. I will go on one by one. So first I will talk about the wall generation part. So suppose a client runs a transaction on the backend process. So what happens when a transaction is running? So for each of the commands, some things will be modified on some of the tables. So corresponding data pages are shared on the the corresponding heap pages are loaded on the shared buffers, and the changes are made, and the pages are marked as dirty. And correspondingly, alongside it, the wall records are also generated and are shared on the and are stored on the wall buffers. And once this transaction is committed, these wall buffers, the wall records present in the wall buffers, are flushed to the disks inside the PG wall folder. And once these changes are flushed, we can say that the transaction is committed, and the changes on the shared buffer can be flushed to the disks at later point of time by check pointer or the background writer process. Once this wall files are generated, the wall sender process will start reading these wall files, and it will also check the replication slot. It will get the values of restart LSN and confirm plus LSN, and it so with the help of the LSN values, it will start reading the wall files, and it will start the logical decoding of the wall files. So the physical changes are converted into logical changes, and then a logical replication protocol messages are constructed, which is sent to the subscriber node. Once it is received on the subscriber node, apply worker comes into the picture, and it will start a local transaction, and it will apply those changes and commit that transaction. Once that transaction is committed, it will update the replication origin on the subscriber node, and alongside it, it will send a feedback message to the wall sender process. And once that feedback message is received by the wall sender process, it will update the LSN values on the replication slot. So this was the basic basic flow it will follow. Now I will go in deep of each of the process, and for that I am using an example. So suppose we are creating a publication on a table called users using this create publication command, and created a subscription at subscriber node using create subscription command, which is subscribing to that particular publication. Now we execute this particular transaction, like so this is begin, insert into users, and then commit. So once this transaction is executed, let's see what happens. So first process, as I discussed earlier, was wall generation. So for each of the commands, some wall records would be generated. So for begin command, it will start a new transaction context, but no, since it has not done any changes to the database, no wall records will be generated for this begin record. And when insert record is when insert command is executed, it will load the required corresponding page to the shared buffer, and it will insert that tuple and insert the tuple in that page, and it will mark the page as dirty. And along with side, a corresponding wall record is generated. Insert wall record is generated and returned to the wall buffers. So at this point, this transaction is only visible. This change is only visible inside this transaction and would not be seen by other transaction. Now, when commit command is executed, the Postgres will append this commit record into the wall buffers, and the walls present in the wall buffer is flushed up to this commit LSN. And after this walls are flushed to the disks, we can say that transaction is durable and is committed. The heap page, which was on which we inserted the rows in the shared buffer, are returned to disks at a later point of time using by the background writer or the check pointer process. And for each of the wall record, LSN value that is log sequence number is assigned, and it helps to identify that particular record in the wall stream. So for our example, we can see there are two wall records generated. One is insert and second one is commit. So for the insert, we can see the transaction ID is 761, and the resource manager identifier which have generated this record is the kind of heap. And the second record is transaction. So it is generated by the resource manager of type transaction, and it is a commit record, and it is also for the same transaction 761. Moving on. So till now we saw that wall files are generated. So in background, so Postgres periodically removes the wall files and also recycles it, or removes or recycle it, and it does it because so Postgres removes or recycle old wall records periodically to prevent unlimited growth of the disks, and it can happen that the old records may be required by logical replication. So how these records are preserved? These are preserved with the help of replication slot. So it ensures that the wall needed for replication is retained until the subscriber consumes it. Okay. Now it have two main fields that are, so for each replication slots we have two main fields. One is the restart LSN, another is confirm plus LSN. Restart LSN refers to the oldest wall record which is required for logical decoding, whereas confirm plus LSN refers to the latest wall location which is confirmed by the subscriber. So latest wall record confirmed by the subscriber means the up to which the changes are applied on the subscriber node. Now let's see about the wall sender process. So wall sender process is a dedicated backend process on the publisher that reads the wall record and sends the logical changes to the subscriber. It is created by the apply worker when requests like start replication requests are sent to the publisher node, and its main responsibilities are to read the wall record from the disks, use the logical decoding context to decode this wall record, then reassemble the transaction using the reorder buffer, and pass these decoded changes to the output plugin, where the output plugin will construct the logical replication protocol message, and then wall sender finally sends that to the apply worker. So let's see about the logical decoding. So logical decoding converts the physical wall records into logical changes. So once the wall records are read by the wall sender process, they are passed through the logical decoding framework, and for each record it is interpreted based on the resource manager which have generated that wall record. And there are different types of resource manager, and for logical decoding we only see some particular type, we only decode some particular types of wall records which are generated by resource manager. So important type of resource manager which generate the wall records and which are decoded by logical decoding are heap or heap2, which generates change which refers to wall records related to row level changes like insert, update, delete. Then second one is of type transaction for like commit records or abort records, and third one is of type resource manager is of type logical message. So this kind of wall records are generated for custom message, like if user want to send some type of custom message, this type of resource manager are used. Now after the wall records are decoded, a logical change is constructed from the tuple data. So raw tuple data is converted into a logical change, and it is stored inside the reorder buffer chain structure. You can I have already shared a like high level structure, like how it looks. So these are some important fields this reorder buffer change have. Now going on, let's see what reorder buffer is. So wall records are written to the disk in sequential order and are also read sequentially during decoding. However, there can be case that multiple transactions are running concurrently, and so due to that the wall records can become interleaved. So here you can see the example, like there are multiple transactions are running and you can see the wall records are getting interleaved. So the main task of reorder buffer is to group the record for each transaction. So how does it do it internally? So it have a hash table indexed by transaction ID, and for each transaction ID it will maintain a list of changes, row changes, and once the commit record is decoded, it will send the entire change, so entire change for this transaction to the output plugin for further processing. And while these changes are are queued in the reorder buffer, it can happen that the memory limit that we have logical decoding mem GUC in Postgres. So if it exceeds that memory limit, the changes are spilled to the disk, and at the commit time it is all loaded back to the memory for further processing. So in latest versions of Postgres, streaming of in progress transactions are supported, but for my presentation I will not talk about that for the simplicity. Now coming back to our example, let's see, like we saw that how wall records were generated. Now I will talk about how wall sender will process each of the records. So first it will read the records, start reading the records. So first record it will get is the insert record, and it belongs to transaction 761, so transaction ID 761. And once the record is read, the logical decoding is initiated. So once it is initiated, it will check that the resource manager which generated this wall record is of type heap. So heap decode function is invoked. Now inside heap decode based on the type of record. So since it is a type of insert record, decode insert is decode insert function is invoked, and it will convert that physical wall record into a logical change. So it will read the raw tuple data in wall, and it will reconstruct it into a heap tuple structure, and it will then store it inside reorder buffer change. Once this reorder buffer change structure is constructed, it will send it to the reorder buffer to store it inside reorder buffer. So since it is the very first record for this particular transaction 761, a transaction entry is created for this transaction, and this insert record is queued inside that particular transaction entry. Now the memory counter of reorder buffer and transaction entry is updated, and then we will check the logical decoding work mem. If the memory limit of the reorder buffer exceeds this GUC value, the largest transaction in the reorder buffer is evicted to the disk and stored in temporary spill files. So till now the insert is decoded and stored in reorder buffer, and nothing is yet sent to the subscriber. Now we process the commit record. So second record generated by wall was commit record. So wall sender will read it, and it is generated by resource manager transaction. And as you can see, I have pasted the commit record as well. So logical decoding for this record is initiated, and corresponding function, that is exact decode, is invoked. Now inside this exact decode, based on what type of record it is. So it is of type decode commit. It is of type commit record. So decode commit function will be invoked, and we will it will extract the commit LSN, commit timestamp and transaction ID values, and it will signal that this transaction is completed, and it will call reorder buffer commit function, and it will notify the reorder buffer that this transaction is committed. So once this reorder buffer commit function is invoked, all the changes for this particular transaction is replayed, and these are replayed in the original order in which they are queued in the reorder buffer, and if any changes are spilled to the disk, they are loaded back into the memory before replay. So while replaying, for each of the record, the corresponding callback function in the output plugin is triggered, and once all the processing is done by the output plugin, this particular transaction entry is cleaned up from the reorder buffer. Okay, till now we saw like how it is processed inside reorder buffer and it is sent to the output plugin. Now let's see what is output plugin. So basically output plugin converts this decoded wall changes into the format that can be sent to the subscribers. So the main responsibility of output plugin is to receive these changes and apply the filters. So it will, so while creating publication, we specify the filters. So that filters are applied inside this output plugin, like column filtering, row filters, if the generated columns are published or not, and what type of records are published, insert, update, delete, or truncate. Based on that, the filtering is done. Once the change passed that filters, then this change is converted into logical replication protocol messages and are sent by the wall sender process to the subscriber. So by default, Postgres has PG output plugin. We also have other type of output plugins such as test decoding, wall to JSON, etc. Now let's see when the changes are replayed inside reorder buffer replay, which all output plugins are called. So for the first change, that is the insert change, PG output change is called, and for this change we will check that this change is for which relation, and we will construct a relation sync entry inside the function getRelSync entry. So this this relation sync entry contains the information like whether this particular relation is published or not. If it is published, what all operations are published, like insert, update, delete, or truncate, which all operations are published for this particular relation, what all column are published, and what all row filters are applied for this relation. And it also checks the partition routing information, if generated columns are published or not, etc. And once this is calculated, this entry is cached so that it can be used in future, and we don't need to reconstruct this again and again. So based on these filters, this change is filtered, and if it passes these filters, it will go for further processing, otherwise it will be rejected. Now for our case, the change passes all the filters and it goes for further processing. So now the logical replication protocol messages are created. So since this is the very first change in the transaction 761, a begin message is constructed and sent alongside. So since this is the first change on that particular relation, a relation message is constructed and sent. This relation message mostly consists of the table schema information, and finally insert message is constructed and sent. So you can see like which all things are present in each of the message. So for begin, we have the final LSN of the transaction, which is equal to the commit LSN for the transaction, whereas second one is commit timestamp of the transaction, third is the transaction ID. For relation message, we have relation OID, schema name, relation name, replica identity, column metadata, column names, column data types, and flags for the columns, like what all primary keys are there, generated columns are there, and information related to replica identity are shared in this particular message. And for insert, we send the relation ID along with the number of columns and the column values for each of the column. Then, so now coming to the processing of the commit in PG output. So till now all the changes, so inside reorder buffer we only had the insert change, so that is processed. And since a commit record was decoded, PG output commit will be invoked now, and PG output commit indicates that the transaction has successfully completed and all the changes inside this reorder buffer for that particular transaction has been replayed. So our commit message is constructed, which consists of this three information: commit LSN, end LSN in the commit timestamp, and it is sent to the subscriber by the wall sender process. After this commit message is received by the subscriber, the subscriber get the idea that, yeah, I can apply that entire transaction locally. Now moving forward, let's see talk about apply worker. So once these changes are sent by the wall sender process to subscriber, it is received by the apply worker process, and apply worker process continuously receive these changes, and based on the type of the message, it will route these messages to the appropriate handlers. So for our cases, we saw four messages were generated, like begin, relation, insert, and commit. For that messages, this particular handlers will be called. Now let's see what all the handlers do. So when this begin message is read inside apply handle begin, it will extract the final LSN, commit timestamp, and the XID of the transaction. Then it will store this final LSN value inside locally for tracking replication progress, and it will use the XID values and the final LSN values to construct the error context for debugging. Now when this relation message is received, apply handle relation is called, and it will read the relation message, and since it contains the metadata for that relation, it will read those values and it will store inside a structure called logical rep relation, and it will cache it inside logical rep rel map entry. So when at later stage, when insert, update, or delete operations are done, it can get the relation metadata information using this cache information. Now we will get the insert message, and when this for insert, this apply handle insert handler is called, and since this is the very first DML operation for this particular particular change which we are receiving, particular transaction change which we are receiving, a local transaction will be started on the subscriber node, and this insert message which was sent by PG output will be read, and the relation map entry which was generated in the previous message will be fetched. Based on this information, a tuple table slot will be created. So with the help of the messages it have read from with the values it has read from the replication message, it will populate this structure with the column values. Then it will populate the structure with the default values, if any. Then it will open the indexes perform the privilege checks, then insert the row using exact simple relation insert, and once it is done, it will close the indexes. Now, the apply worker receives the commit message, and for that it will call the corresponding handler, that is apply handle commit, and this function will read the commit message and get the LSN values, commit commit LSN, end LSN, and the commits timestamp, and it will check if the commit LSN and the final LSN which was received during the time when begin message was read, and it will match it. If the mismatch occurs, it will throw an error, otherwise it will commit the local transaction which was created by the insert message which was received, and once this local transaction is committed, the replication origin progress is updated. Okay, now once this is updated, the feedback loop comes into picture. So after the commit, subscriber will send a feedback to the publisher, and this informs the vault sender that the changes are applied, and it will instruct the publisher to update the confirm plus LSN value in the replication slot for that particular subscription. Finally, the changes are replicated to the subscriber. Now, so in the previous slides, we saw how the insert record is sent from the vault sender to the insert record is sent from the publisher node to the subscriber node. Now for update and delete, it follows a similar life cycle, but so apply worker does not know, like when applying the changes, that which rows it should update on the subscriber node or update or delete. For that, we send a replica identity information alongside it alongside. So we set the replica identity for the tables. So with the help of the replica identity, we can uniquely identify a row, and the update or delete operations can proceed. So there are 4 types of replica identity. One is the default, which uses the primary key of that table. Second is the index. So we can create an index, and we can specify that for replica identity, use this particular index, and we can also specify full. So replica identity will be set to all the columns for that particular relation, and the 4th one is nothing. So do not specify any replica identity. In this case, update or delete operations can't happen. So this was the talk, and here are the references which I used. Yeah, thank you.